Hi, my name is Tejish Achari. My roll number is 20951A04M0 and I am from ACT section. And my topic is how to estimate the specific heat capacity and heating of electronic sensors and devices. So most sensors have three functional parts: the sensor part, signal conditioning part, and interface part. The sensor part senses the physical phenomena and transforms it typically into electric form. The signal condition part amplifies, linearizes, and scales the electric signal. The interface part can be a simple mechanical connector, field, bus adapter, or in a wireless sensor, a radio module. Signal conditioning and interface paths are in most cases implemented by electronics. Standard electronics can operate in quite a narrow temperature range, about -30 to +125 degrees Celsius. This limits use of electric sensors, especially in industrial sensor applications. In the process environment, there are many places where temperatures temporarily or for a long time exceed the highest tolerable temperature of electronics. Even continuous high temperatures under +125 degrees Celsius cause severe disability of electronics, such as increasing leakage currents, decreasing power handling capacity, lowering operation speed, and finally degrading electronics, which leads to damage. So much research work has been done to develop electronics that tolerate temperatures more than the standard electronics tolerate. High temperature electronic devices HT can operate for short times in temperatures of +485 to +600 degrees Celsius. HT components available today are passive components and some diodes and transistors. In addition, surface acoustic wave SAW components are auspicious, having temperature ranges up to +100 degrees Celsius. However, all active sensors using standard electronics and operating even for a short time in high temperatures +200 to +1300 degrees Celsius in industrial environments, especially in furnaces, must be protected by thermal insulation and, when possible, by active cooling. Unfortunately, an enclosed sensor located in a high or moderate temperature area, example from -30 to +100 degrees Celsius, is threatened by internal heating when operating actively or with high power. This self-heating happens due to the power consumption of the device. The heating speed is mainly dependent on the heat capacity of the device, enclosure material, and power dissipation of sensor electronics. Wired or wireless connection to processor user. So, like the interface part, the signal conditioning part, the sensing part, the physical world, the whole process, how it happens. This article studies the specific heat of electronics by reference to theory and empirical tests. An experimental value for the specific heat capacity of standard electronic components is determined. The value can be used for estimation of heating of electronics in a closed case. The second part of the paper focuses on modeling, simulation, and empirical tests of heating of electronics in a closed insulated enclosure. Specific heat. To understand the warming mechanism of sensors and electronics, a short theoretical introduction to some thermal issues such as heat capacity, thermal flow, and resistance is necessary. The temperature differences between objects at unequal temperatures tend to equalize due to transfer of energy from the warmer to colder object. This transferred energy is called the quantity of heat. This energy does not mean the energy of a system, it only represents the transferred heat energy. The unit quantity of the energy is a joule. Transferred heat energy is designated with the symbol Q. For very small or infinitesimal amounts of heat, dq, heat capacity can be defined CdQ dt. Estimating heating of a sensor device to demonstrate the heating of electronics closed in an insulating enclosure. A spherical sensor enclosure was made. The material of the enclosure was insulation board Super 1100E, manufactured by Swedish manufacturer Skamol AYB Limited. The company produces many kinds of insulation products. Super 1100E contains silicon dioxide SiO2 47% of mass, calcium oxide CaO 43%, and some other materials. The maximum operating temperature is plus 1100 degrees Celsius. The specific heat value is 0.884 kilojoules per kg Kelvin. The thermal conductivity is low, starting from 0.08 W by M star K at and under plus 200 degrees Celsius to 0.14 W by M star K at 800 degrees Celsius. The material is easy machinable. The outer diameter enclosure was 95 mm. The diameter of the inner space was 45 mm. So, the summary: industrial sensors are often located in places where external cooling or ventilation is inadequate for keeping sensor electronics at low enough temperature. In addition, self-heating adds the risk for overheating and failure mechanisms arising from it. Much scientific work is being done to extend the range of operation temperatures and the lifetime of electronic devices. However, there is not yet any technology capable of functioning in combustion temperatures from plus 850 to 1300 degrees Celsius or higher. In this paper, the heating of a sensor in a protective and closed enclosure is studied. The study is part of research work for intelligent, short life, time mobile sensors for combustion areas and temperatures. The first conclusion is that when a closed enclosure without any external cooling is used, the specific heat capacity of the electronics must be known to be able to calculate estimates for their lifetime before thermal breakdown. An estimate of the specific heat value of a small lot of electronics was determined in the paper. The resulting value of about 0.69 kilojoules by kgk, while set dependent, can be considered broadly representative. Total inaccuracy of the measurements was below 5%. However, one must keep in mind that measured value is strongly dependent on the component set used in the test. The value found can be used to calculate initial estimations of the heating of electronics in a closed enclosure when no cooling is possible. Such situations can occur, for example, when mobile sensors are used in hot environments. In practice, electronics in closed enclosures without any cooling will get too hot and destroy themselves. If the enclosure can transfer heat from the outer surface to the temperature inside the enclosure, will stabilize to a value related to the power inside the enclosure. So there's a graph showing how that's going to happen. So thank you.